This conference will now be recorded.
Hello students. So yesterday we had started with interference of light. So we have been discussing about the conditions for constructive and destructive interference. So I hope you remember what is called constructive and what is called destructive interference. So as we have discussed, interference means overlap or superposition of waves. Okay, but in that case we had discussed that the waves should have come from two coherent sources and they should maintain a constant phase relationship, then only interference will happen, otherwise it will be a general illumination. So we were trying to find out the mathematical expression for the intensity at constructive interference and destructive interference. So where the waves are meeting at phase, okay, in phase, their intensity will be maximum intensity of the light, and the region where the two interfering wave meeting at meeting it out of phase, then we'll get minimum intensity. So that is what we are trying to see mathematically. So yesterday we had somewhat discussed, but still I just would like to recap that little bit, and then we will try to find out the conditions. Okay, let us start then. So let us suppose there are two interfering waves. So suppose these are two interfering waves and they are meeting at some point P, and suppose this wave has a displacement y1 and this has y2, and they maintain a constant phase relationship phi. So how can we write those? Suppose y1 is a1 sine omega t, and the other wave has displacement a2 sine omega t plus phi. This phi is constant phase between them. Okay, this phi doesn't change. We'll just discuss one by one. Let me just do the underlying mathematics over here. So interference, when it happens, like when they overlap with each other, according to the principle of superposition, what happens? So y is equal to y1 plus y2. Okay, so that we had done already a little bit. So we have to use some trigonometric identity to make a little bit simplified form. So this we have to bring as a single sinusoidal or cos, like a single sinusoidal term. So for that, what we'll do, let us just write in terms of so this part actually we can use trigonometric identity sin a plus b. So then we can write, so if I say this is a, this is b, so sin a cos b, sin a cos b plus cos a sin b, cos omega t sin phi. Okay, this is what it is. Now look what we can do. We can take the sine terms together. So sin omega t, if we just take together, then see the coefficient of that will be a1 plus a2 cos phi, okay, into sin omega t, and this side it will be a2 cos omega t sin phi. Okay, so this is the term. Now So just a minute. Madam, am I audible?
Yes, yes.
Okay, shall I continue?
Yes, yes, you
Yeah.
continue.
So here we have to make in terms of sine or cosine term. So what we can do, we can just take this as, let us say, this particular term as this one, a1 a2 cos phi. If we just consider this as a cos of theta, and this term a2 sin phi, a2 sin phi, this particular term, let us take this as, this I'm putting, okay. So put a1 plus a2 cos phi is equal to a cos theta, a2 sin phi as sin theta. Now look, if we just put it here in this, what we will get? The resultant one will be, see, this term we have taken as a cos theta. So we'll write, instead of writing this, we'll write a sin theta, sorry, a cos theta sin omega t. Similarly, for this, this a2 sin phi we have taken as sin theta. So we'll write a sin theta here, and cos omega t was there already. So look, then what we are getting, a is common. So sin a cos b, I take this as, so sin a cos b, cos a sin b. So it is actually coming as sin omega t plus theta. So you can see here the interfering wave is also a sine curve like this. Okay. Now see, from here we have to find out amplitude. See, this a is not known to us, isn't it? So ae, see, a1 and a2, these were intensities, like amplitudes known to us, because we know two waves, they have certain amplitudes. But this is the resultant one. We don't know this, so we have to find out this. A is, a could be found out writing this a square. See, if I just square these two terms, a1 square, let me just write in elaborate. So a1 a2 cos phi, okay, this square plus a2 sin phi. I'm just squaring them out. See, we had taken this to be a cos theta, so a cos theta square plus here it will be a sin theta square. Okay, then I have added. Okay, so this will give you a1 square plus 2a1 a2 cos of phi plus a2 square cos square phi Here it is a2 square sine square phi. Okay, now this side it will be a square. Okay, look, if we simplify this term will give you a2 square alone, because a2 take this a2 common. So sine square theta plus cos square theta will be 1, isn't it? So you get a1 square plus a2 square plus 281 a2 cos of phi. This is equal to a square. So you get this amplitude like this. Okay, see, now at this position I'll tell you one thing. I think yesterday also I had discussed somewhat. So amplitude and intensity, they are related to each other. So intensity of light is directly proportional to the amplitude square. So what we can write, I intensity is equal to k a square. K is the proportionality constant. So if we write for this equation, look what I can write. This I can write I1, that means intensity of the light coming from intensity of the light associated with the first wave, and this is intensity of the second wave. Sorry, not square. Okay, if I just multiply k on both sides, so we can write that, isn't it? This also I write k, and here also. Then I can write easily, right? This is k a1 square means intensity of the light 1, wave 1, intensity of the wave 2, and see this I can write 2 root over k a1 into root over k a2. Okay, sorry, root over i1, root over i1, root over i1. See, if I write root over k into root over, okay, let me make you again clear here, just a minute. See, this term I'm writing here as root k a1 whole square. Okay, again this is little wrong. Let me, actually square will be inside, k a1 square, root over k a1 square, so that, okay, just a minute, 2 k a1 square, now it is okay, k a2 square, okay, like this, into cos phi. Okay, so let us just rewrite everything what we have got here. Is, see, I have got the equation as a sine of omega t plus phi. This is the resultant wave, where a we had got square root of a1 square plus a2 square plus 2a1 a2 cos phi. Okay, now intensity, resultant intensity, we get I is equal to I1 plus I2 plus root over I1 I2 into cos phi. Okay, so this can be written like root over I1 into root over I2 also separately. Okay, so you can see here, this is intensity of the individual waves. These two are okay. This is for wave 1, this is for wave 2. Now this is the overlap term. This is called interference term or overlap term. Okay, interference or overlap term, because there is product of the intensity of both the waves, isn't it? Okay, overlap term. So this is actually give you, so this is only giving you the interference or stating you about interference. See here, this cos phi is actually, this is the constant phase between, constant phase difference between the waves. Okay, interfering wave. Okay, waves. All right, now let me, okay, I think I have to erase, keeping this only this part. Okay, keeping things only this part. Let me just go here. I is equal to I1 plus I2 plus 2 root over I1 into root over I2 cosine of phi. So here this term, this cos phi, is very, very important, because interference depends on whether, okay, so interference depends on this phi alone. Okay, now first of all let me tell you, see if this phase, see cos phi, if this cos phi changes randomly, what happens? If it changes randomly, then if we take the average of that, that will give you 0. Okay, that will give you 0. 0 means this interference term will not be there in the intensity. So then you know what happens. Suppose you have two candles. Okay, two separate candles kept side by side. Okay, so this has intensity I1, this has intensity I2, but these are not coherent sources, as I said. So in this case, you know, you will get total intensity as I1 plus I2. This is not the interference phenomena, because this interfering term is not there, overlap term is not there. So just simple algebraic sum of the intensities of these two. Okay, this is not interference, so it will not. So see, if the sources are not coherent, that means if they don't maintain a constant phase relationship, then the phase will change continuously, and when you take the average of this cos phi, then it will give rise to 0. Okay, if the phase is changing continuously or randomly, then it will give you 0. Average of cos phi will be 0, hence there will be no interference, and then what you get is called general illumination. Okay, this is called general illumination. Just like you switch on two bulbs together, you get intensity little greater, but this is not due to interference. Okay, if there is interference, what will happen? Yesterday we had discussed, if interference happens, you will see dark, bright, dark, bright. See, this is, suppose this is bright and this part is dark. So dark, bright patterns you will get if there is interference happening. Okay, all right, now we'll see where the constructive interference happens and where the destructive interference happens. So we have seen that interference will happen only when there is a constant phase relationship between the interfering waves. Okay. All right. Now we'll see there are two types of interference we have seen, that is constructive interference, that means intensity will be maximum, and destructive interference means intensity will be minimum. So look this expression. So maximum and minimum value of this intensity depends on cos phi. Suppose, okay, so condition for constructive interference. Constructive interference means maximum intensity. So I will be Imax, okay, when cos phi is what? Cos phi is 1 plus 1, okay, cos phi is plus 1. When cos phi is plus 1, then only we will get maximum intensity, resultant intensity at the point of interference. Okay, so for that case, you know what will be the maximum intensity? It will be C root over I1 root over I2 whole square. Is there any problem? So if cos phi, see here, cos phi is 1, that means it will be root over I1 plus root over I2 whole square. Okay, so this will be actually maximum intensity if cos phi is 1. Okay, so when cos phi will be 1, so cos phi is 1. Okay, this implies that phi must be 0 or plus minus of 2 pi or plus minus of 4 pi or like that, plus minus even pi. Okay, plus minus even pi. Okay, 2n pi I can write. N is general integer, okay, integer number, so 2n pi. Okay, so the interference will be constructive in nature if the phase difference between the interfering waves is, phase difference means, see, this is phi, no, so we have taken the waves as one as sin omega t, another one sin omega t plus phi, so delta phi is phi only here, so phase difference is phi, isn't it? Phase difference is phi, so this phase difference has to be integral multiple of 2 pi. Okay, 2 pi corresponds to, now see, if I write in terms of path difference, see, phase difference and path difference, I told path difference is, sorry, phase difference is 2 pi by lambda into delta is equal to 5. Okay, so when the phase difference is 2 pi, that means I'll write delta pi here 5. So then, so if this is 2 pi, then we'll get 2 pi into lambda by 2 pi. Okay, so path difference is becoming lambda. When it is 4 pi, path difference will be 2 lambda. When it is yes, when it is 6 pi, then we'll get some other number. Okay, 6 pi means here 3 lambda. Okay, so integer number, you can see that lambda, 2 lambda, 3 lambda, 4 lambda, 5 lambda, etc. we will get. Okay, so if we write in terms of phase difference, then the phase difference has to be either 0 or plus minus 2 pi, plus minus 4 pi, etc. Okay, so lambda also will be plus minus lambda plus minus 2 lambda in terms of path difference if we write. So I'll write one sentence over here. See, hence the resultant intensity at any point will be maximum when the path difference between two superposing waves is even integral multiple, like even multiple of pi phase difference, or path difference has to be integral multiple of lambda. Okay, this is condition for constructive interference. So I can write it here. Hence, the resultant intensity at any point is maximum if the phase difference between the superposing waves is an even multiple of pi, or path difference is an integral multiple of lambda. Okay, at that point. Okay, all right. So this is the condition for constructive interference. Okay, so this is condition for constructive interference. Condition for constructive interference. Okay, so this is the resultant intensity at any point is maximum if the interference between if the phase difference if the phase difference between the superposing wave is an even multiple of pi, or path difference is an integral multiple of lambda. Okay, so that means pi must be 0 or 2 pi or 4 pi, etc. Okay, or delta path difference must be, actually there will be plus minus, so 0 anyway, there is no plus minus. So this 2 pi, if we take 2 pi minus or plus, whatever it is, so on both sides you will see. Okay, so this could be 0 or lambda, 2 lambda, 3 lambda. So this is actually integral multiple, not half multiple. Okay, so this can be written as delta should be n lambda. N means integer number, and this is even, not even, so all the natural numbers will come 1 2 3 4, but it has to be integral number. Okay, not fractional. So that is what was here. See here in this figure, the locus of the points for locus of the points on which you will see the maximum intensities have been shown here according to path difference. Okay, in terms of path difference, these are intensity, this is intensity. In terms of path difference, you look how it looks. Okay, the locus of the points for which path difference is, see, path difference is where the path difference is 0 or plus minus lambda or plus minus 2 lambda, like that it is shown here. N lambda means, right, see, n plus minus n lambda you can say. So n lambda both side. Okay, both side you can see this is the middle portion, n is equal to 0. So n1 2 3 here n is equal to -1 -2, and see all the points has actually path difference minus lambda. N is 1 here, all the points have path difference minus 2 lambda. Okay, here on this path, on this curve, path difference is lambda, and here 2 lambda, here 3 lambda, etc. Okay, so this is condition for constructive interference. Now we'll see the, okay, so here before I go to this topic, let me find out condition for destructive interference. Destructive interference. Okay, destructive interference. So what is the condition? Same thing, we have to actually check here when the intensity becomes minimum. In case of destructive interference, intensity has to be minimum, right? So it is minimum when, so I will be I minimum when cos phi will be is equal to -1. Okay, minimum only when cos phi is equal to -1. See that time the intensity will be I is equal to I1 plus I2 minus 2 root over I1 root over I2. Okay, so this will give you I1 minus, sorry, root over I1 minus root over I2 whole square. So this is the minimum intensity. Okay, this is the minimum intensity. All right, so what will be the condition here? At what condition this will happen? As I said, cos phi has to be -1, and when cos phi will be -1, let me write here. See, cos phi will be -1 when we write, like, phi is odd pi's. Okay, for all odd pi's, so cos phi is equal to -1 implies that phi is plus minus pi or plus minus 3 pi plus minus 5 pi, all odd pi's. Okay, that means, you know, I had written that time 2n pi, so here it will be 2n plus 1 pi. Okay, 2n plus 1 pi. All right, so for all odd pi's we'll get -1. So this is the phase difference. So in the phase difference become like this. So phi here, phi means delta phi itself. Okay, phase difference. So so in terms of phase difference, this is the condition is this is phase difference. Phase difference has to be plus minus pi, plus minus 3 pi, plus minus 5 pi, etc. Okay, but what about path difference? So if path difference is, see, path difference 2 pi by lambda into path difference will be suppose pi. So in that case, you know, delta will be lambda by 2. So for other one, see, for this one, delta will be then 3 by 2 lambda. For this one, delta will be 5 by 2 lambda, right? So like that, this is, see here, the destructive interference will happen when the path difference is half integral of the lambda, okay, wavelength. Lambda is the wavelength of the wave, okay. Hence, the resultant intensity at any point will be minimum when the phase difference between the superposing waves is odd multiple of pi, or the path difference is an odd multiple of lambda by 2. Odd multiple of lambda by 2, you can say odd multiple of lambda by 2, or odd half integral. This is of half, odd half integer number, okay. See here, 1 into lambda by 2, odd half, okay. Then odd half lambda, okay, odd half lambda, odd number with half lambda, okay. So path difference has to be an odd multiple of lambda by 2, okay. At this condition, the destructive interference will occur, okay. So in this phase, okay, all right. So this is see, if this okay, this conditions actually we can write in a little bit fancy manner. I just erase everything here. This you can note down later from the video, okay. Just a minute. See here, condition for, so phase difference delta pi or pi, whatever you say, this has to be pi, 3 pi, 5 pi, like that, any odd pi, okay, 2n plus 1 pi, any odd pi, okay. And in case of lambda, path difference, in terms of path difference, so delta has to be lambda by 2, then 3 lambda by 2, odd multiple of lambda by 2, that is what we are saying. So 5 into lambda by 2, okay. So this, then it goes like this. So in general, not plus, that means this, and here also we can write 2n plus 1 into lambda by 2, okay. So this is what we can do. Hence the intensity will be minimum, or this is the condition for destructive interference, okay. I'm not repeating again. So these are very important points for exam purpose, okay, for exam purpose. See these patterns, you know, these patterns. So this is bright, these are maximum intensity, okay, having maximum intensity. This is called first order interference wave, this is second fringe, this is called third fringe, okay, like that. We'll discuss fringe, what is fringe, etc. Yeah, okay. Now we'll discuss about Young's double slit experiment. So Young was the first scientist to claim that light is wave, okay. This is actually, he was a British scientist during 1801. So at this era, there was influence of other persons like Newton. So it was very difficult to establish the wave theory of light, but Thomas Young was so intelligent that he could demonstrate the wave nature by doing this experiment. Very simple method of doing this experiment. Okay, very simple manner. I think I just meant to say very simple arrangements or apparatus he had taken, and then he had actually demonstrated the interference experiment. Okay, so Young's double slit experiment is on the interference phenomenon. Okay, interference phenomenon. So when he could demonstrate interference phenomenon by doing this, and see, we'll be explaining this interference phenomenon in terms of wave theory. So he could actually establish that light is having wave nature. Okay, wave nature. So that is what light is not a ray or not a classical particle. Light is actually a wave. Okay, so that is what was established from this experiment, and it was really very important. And also what to say, this is really very great achievement, okay, during this time. All right, so here I just discuss what Young had done first of all to demonstrate this experiment in the lab. Okay, in the laboratory, what he had done, he had taken his point source. See, he had taken sodium lamp. Okay, sodium lamp, and then he had, so this is kind of a cardboard. Okay, cardboard. Okay, made a very tiny hole, the pin hole you can say. He made a pin hole over here. Okay, so sodium light can be easily found out with a single wavelength. Okay, or monochromatic sodium light, we can say monochromatic sodium light. Excuse me. Monochromatic sodium light he had taken and illuminated this pin hole made on the cardboard. Okay, and then see, since this is a hole, there will be light passing from here, and see, at certain distance he had taken another cardboard. Okay, he had taken another cardboard, and he had made two parallel holes. See, S1 and S2, two parallel holes on that cardboard. S1 and S2 are the parallel holes. Okay, so these holes were illuminated by this S0 source. See, S0 is the main pinhole. Okay, this acts as a source here, source for illuminating this S1 and S2. These are called slits. Okay, S1 and S2 are called slits, and this is called actually source S0. This is a pinhole made on the cardboard, and this pinhole or this was illuminated by monochromatic sodium light. Okay, so monochromatic sodium light comes as plain wave. You can see that these are the wave pattern, like wave font, plain wavefront. But when it passes through this point source, now it has become a point source here. So light waves will be actually emanating from each point of the slits as a spherical wavefront, and then that spherical wavefront will be progressing up to these slits, S2 and S1. They will be illuminated, and each point on the slits will be acting as point source according to Huygen's principle. Okay, secondary sources. Those secondary sources will be producing secondary wavelets, and these wavelets from S1 and S2. Now see, just beauty of this, making the slits illuminated by single light. You look here, the sodium light is passing through S0 or SO source, then this is illuminated. See, S2 and S1 are illuminated by this same light, or light coming from the same source. So in this case, see, coherent sources, this S1 and S2 are coherent sources. S1 and S2 are coherent sources because they are illuminated by same source, illuminated by same source, same source. Now whatever abrupt phase change occurs in the source, that will be manifested in both in a similar manner. Then ultimately phase difference will be constant only always. Okay, so whatever abrupt phase change occurs at the source, that will be manifested into equally. Okay, so that's why this S1 and S2 are actually coherent sources. Now see, spherical wavefronts are uh, emitted by each secondary sources, and those secondary wavelets are now, see here, secondary wavelets from two slits are interfering, and when they interfere in phase, or phase difference becomes 0 or integral multiple of or even multiple of pi, then they are called in phase. Okay, that means delta pi is into even multiple of even integer. Okay, even multiple of pi, even multiple of pi. Okay, even multiple of pi. So then what will happen? Intensity will be maximum at that point. So look here, these are having maximum intensities. So this alternate, see in the screen, this is the screen. He kept screen after this slits. He had kept at certain distance, and this distance is generally denoted by capital D, and the distance between these slits are actually denoted by small d. Okay, this is in general. Okay, now on the screen what we see? We see alternating bright, dark, bright, dark. See maximum intensity, minimum intensity. So this is minimum, this is maximum, again this is minimum. So we see alternate minimum and maximum, or we can say alternate dark and bright fringes will occur, not bright and alternating bright and dark regions are seen in the screen. Okay, and see this bright region or dark region, they are a little bit spreaded, so these are called actually fringes. Okay, these are called fringes. So bright fringe and dark fringe. Okay, we say dark fringe and bright fringe. Okay, so you can see, so I hope you have understood now the explanation of this bright and dark fringe, why this interference happens. So in the interference we will see bright and dark regions. Okay, alternating dark and bright regions upon, so this comes from interference. You have understood when the two overlapping waves are meeting and in phase, then or the phase difference becoming in even multiple of pi, that time intensity will be maximum. When the light waves are meeting out of phase, that means delta pi will be odd pi, odd multiple of pi. Okay, as we had discussed in the previous discussions, in the previous slides. Okay, odd multiple of pi. So in these cases there will be dark regions. Okay, dark regions are this, or minimum intensity. So alternating bright and dark fringes will be seen in the screen. So this is, see, since this region is spreaded over, so these are called fringes actually. Okay, dark fringes, bright fringes. Okay, and the width of this fringe, see fringe width, see if we take the difference between, or the space or the difference between consecutive fringes or fringes gives the fringe width. Okay, that gives fringe width. So fringe width is the separation between two successive bright or dark fringes. Successive dark or successive bright fringes. Okay, so this is bright fringe, this is bright fringe. So separation between them is this one. So this is called fringe width. Okay, I'll just write it here. Fringe width. So we have discussed what is called fringe and fringe width. So what is fringe width? We have to now find out the expression for that fringe width. Okay, we have learned what is interference, so we have learned the underlying theory. So what happens, we have already discussed. So from the source, single source, we are making two sources, two slits, S1 and S2. These are illuminated by the same source, so these will act as coherent sources. These are point sources, and each point on the slit will act as secondary sources, and they will produce secondary wavelets. Those will be spherical in shape, and those spherical wavelets or spherical wavefronts will like overlap on each other. See, these points are overlap points, you can see. So these are overlap points. Okay, these are overlap points, overlapping. Okay, these are overlap points. So at these places there will be bright or dark regions. Okay, where they overlap, there will be bright or dark regions. Okay, bright regions are called bright fringes and dark regions are called dark fringes. Okay, bright fringe or dark fringe. And the separation between successive bright or, so the separation between two successive, okay, between two successive bright or dark fringes is called fringe width. Okay, it is called fringe width. Now look, we have to find out. See, one thing you can see here. So these bright regions, these are, see, these are dark regions. So minimum. So intensity can be, this is actually intensity plot. Okay, intensity plot. So let me just explain once again here. So what we have here, we have source, we have two slits, and this is screen. This is screen. Okay, so we need to find out the relation between fringe width. Fringe width is actually denoted by beta, and see, this is the central point. Suppose this is the source, these are two slits, and this is screen. Screen you can see here, right? So if the wavelength of the monochromatic light we used is lambda, fringe width is beta, then at which places, which positions the bright fringes, at which positions the dark fringes will occur. Okay, first dark fringe, first bright fringe, second dark fringe. See, at the middle, see, path difference between, see, at the middle, path difference will be same for both the light. Okay, at the middle, path difference will be same. Okay, path difference will be same. So at this place, actually, there will be a bright region at the central point on the screen. And as I was showing you the locus, so here also on both sides you will see dark bright regions from the central point. Okay, on the screen. So central point means what? This is the line which we have drawn from the middle point between the slits to the screen, middle point of the screen. Okay, that is actually, see, this is the line, this is the line, this is the middle point of this. See, if this is d by 2, this much is d by 2. Okay, this much is d by 2. Okay, this much is d by 2. So if we right? Actually, this is called perpendicular bisector. If we draw a perpendicular bisector from O to this slit width, okay, slit width D, or S1, S2, on the line S1, S2, then we get this, see, OQ. This OQ line actually bisect the screen also, so this O point is central point on the screen, and how you look the intensity pattern, this is the intensity pattern. So in each case, see, first bright, so first dark, then first bright, first dark, first bright, second dark, second bright. Okay, dark will have zero intensity and bright will be having the same intensity. Okay, look, this bright fringes are having, all of them having same intensity. Okay, same intensity. This is one important like point, that in case of interference, intensity of all the bright fringes will be the same. In case of diffraction, it is not. Diffraction, central is maxima, then you will get first minima, then you will get secondary maxima, like that. So secondary maxima, all the secondary maxima doesn't have the same intensity, neither all the minima has, minima anyway zero intensity, but all the maxima will not have the same intensity. But in this case, in case of interference, all bright fringes will have same intensity. Okay, same intensity of light. That is why this is actually see, this is drawn like this. All right, so we need to find out, see, this is, see, if I say this, the distance, if I say this O point is actually origin, and this OP, this is representing y-axis, okay, or OD representing y-axis, and horizontal direction is actually for x-axis, then you know what happens. We can find out the distance where the bright or dark fringes will occur. See, like, see, this OD1. So this distance we can find out. So let us say that is Y1, okay, or OD2, OB1. This distance also we can find out, okay, Y2. Like that, we can find out the distance from the central point, okay, or central bright fringe. And so, as I said, at this point, a light will meet without any phase difference, so there will be always the highest maximum intensity, and that is called bright central fringe. And this will be little bit, okay, so this will be having maximum intensity, bright central bright. It is called central bright, but in the intensity, you know, the intensity will be same for all the bright fringes. So this is central bright fringe. So from the central bright fringe, we can find out the distance, like above this central point or below the central point. So how to do that? For that, let me just explain this. So this is this block, the schematic diagram which I am actually representing, with which I am representing the Young's double slit experimental setup. See here, there are two slits, S1 and S2. These slits are illuminated by a monochromatic light of wavelength lambda, say, and the slits are separated by small d distance, and there is a screen on which we can see the dark and bright fringes. So that screen is d distance, a capital D distance away from the slits. Okay, now we have to find out the beta, and in terms of beta, in terms of lambda, d, these are known quantities. So beta has to be found out from small d, capital D, and y. Okay, so let us do that. See, we have already learned that if we can find out the path difference, then there could be a possibility. See here, possibility to find out the positions. Okay, path difference is the S1 and S2. Let me first S2 minus S2 difference S1 P. You take here minus itself. Why to complicate? So path difference between the interference at this particular position, point P, we want to know whether there will be a bright fringe here or dark fringe here. Okay, this distance I can measure, right? Y. So at this position, whether it will be bright fringe or dark fringe. So how to do that? That we will do here. First of all, we have to find out the path difference. Suppose path difference is S to P. S to P, you can see this point is P, right? So where the light are interfering, light waves are interfering. S to P minus, let us take minus S1P. So this will give you the path difference. So this how do we write? How do we write here? S1P, S2P, we have to find out. This is actually path difference delta. Once you find out this, there will be many things to understand again. Okay. So look here, I will actually consider two triangles. Okay, I will just consider two triangles to find out what is S2P and what is S1P. So S1P is this, so I can just take this triangle. I can take another triangle, this one. Okay, this one also we can take. All right. So let me find out the path difference. So from the triangle, S2P, sorry, S2BP, S2BP, this triangle, S2PB, right? PB itself, S2PB, and S1AP, S1AP, this triangle, as I said. So from these two triangles, from these two triangles, I can write, see, this is hypotenuse, so I can write S2P square S2P square is equal to, or S1P square. Okay, let me first write what is S2P square. S2P square means S2B plus BP square. This is 1. This is 1. And what is S1P? Similar pattern you have to write from this triangle. So that is S1P whole square plus AP whole square. AP whole square. Okay. AYP. Sorry, AYP, not AYP, AP whole square. So these things, you know, I have to find out actually S2P minus S1P. So look what I can write. S2P square means S2B square BP square minus okay. So if you don't remember, you don't have to remember, but you have to just try to draw this figure. Now this S2B and PB. So PB means what? PB. This much is actually D by 2. So this is Y up to here, Y plus. So S2B. S2B is this capital D. So D square plus, see this is Y plus capital, sorry, small d by 2 whole square. Okay, and this minus S1 A square, S1 A square is equal S1 square, yes, plus CAP or PA. This I think S1A we can write directly D square, and this PA this could be written as Y minus D by 2 whole square. Okay, now if you simplify after squaring out or whatever, if we simplify, I think we have to make some assumption here. Okay, later on we will make some assumptions here. So if we just do the simplification, what we will get? 2yd here, 2yd by capital 2D. Okay, 2yd. This is actually, this is square. So this I can write here S2P plus S1P. Okay, so this actually we can do one thing, we can write S2P plus S1P into S2P minus S1P. This is equal to 2yd this is small d, actually small d. The simplification, this one, see this one we need, but this one is what, since this point is very near to O, A point is very near to O, or sorry, P point is very near to O, then this S1P S2P can be written as equal. S2P is equal to S1P. This we can write. S2P and S1P are equal almost. So this term I can write 2D. S1P is also S1P and S2P. These are actually very near to O. See, this P point is very near to O. Then it is 2D here. Here S1P we have to find out S1P and S2P. Let us write it here. S2P minus S1P. This is equal to 2y small d by capital D. 2y small d by capital D. Capital 2D, sorry, capital 2D. So 2D means, you know what you get? You get y into d, d into y divided by capital D. So this is what? This is actually the distance. So this is actually, sorry, this is path difference, okay? This is path difference. Now I can write this as C delta. Path difference delta is equal to small d by y into small d by d. Okay, small d by d. X or y into small d by d. So this is path difference. So for bright fringes, it will be L lambda. This will be equal to L lambda for bright fringes, and for this is for bright fringe. Okay. So for bright fringe, path difference is yd by capital D. This has to be equal to L lambda. Okay. So from there we can actually find out the position y. So d lambda n into d lambda by small d. Okay, d lambda by small d. So this is what we can find out. See, if you put n is equal to 0, 1, 2, etc., we'll get different positions of y. So n is equal to 0 means 0th order or central fringe. So that is y is equal to 0. That is okay. So we have found out the positions of the bright fringes. We can find out similarly position for the, this is position for bright fringes. Okay, position for position of bright fringes n into d lambda by d. Okay, for finding out dark position for the dark, say we get here dy d means small. Actually, this should not be misunderstood with calculus. So this is y into d. This should be actually 2n plus 1. 2n plus 1 lambda by 2 path difference. So y has to be d by small d 2n plus 1 into lambda by 2. So this can be further simplified like this. So lambda by 2, sorry, 2 we can just divide with that. So we get n plus half lambda by 2, sorry, lambda into d by small d, or n plus 1 lambda generally we write d lambda only. N plus half lambda. N plus half lambda. Okay. Now look, if we want to find out what is fringe width, so we have got yn position or bright fringe, yn for nth bright fringe. We have found out n lambda, sorry, n into capital D lambda by this. And position of the dark fringe is n plus half. I have written, right, n plus half lambda d by small d is common. Now if you want to find out what is the fringe width for dark or bright one, first dark fringe, okay, so we have to actually uh, take the difference between two successive bright fringes. The region will be there, right? In both cases, n can be any number 1, 2, 3. Okay, so fringe width beta is actually between two successive. So if we just do that, for nth one, so if we can do it for first one, okay. So first one is n is equal to 1. N is equal to 1 you put here, n is equal to 2 put, so 1 and 2, so 2 lambda by so you will get actually n to n. N is equal to 1 you can put, n is equal to 2 you can put, so we can put n is equal to 1 and 2. See, if we put n is equal to 2, then 2d lambda by small d, and if the second one, I don't know why I have written this, n is equal to, oh, this is d lambda, capital D, and n is 1 anyway, we are not writing, so here, I'm sorry, here it is d lambda by d, and here it is n plus half into d lambda by small d. This will be common, so I have to take the difference between them. So d lambda by small d, 1 minus this one, n is equal to 2 here, right? N is equal to 1, I'm sorry, this is n is equal to 2. This is not for odd, I just write difference between two successive bright. So this will be 2 lambda capital D by small d only. Okay, so you get, ultimately what you get is, I have to take the mod, let me take the mod itself. So you'll get d lambda by small d. Okay, if we want to write, this is for dark, okay, dark fringes. I have taken two successive bright. Now for dark, beta dark, I have to take successive bright. Okay, two successive bright I will have to take for dark. Oh, this is also beta for bright. I will write. Yeah, I'm sorry. Beta for bright. So we have got beta for dark as d lambda by d, and beta for bright we have to take. See, I have condition for bright fringes at the position. Okay, position for the bright fringes we have got. What we have got? N plus half lambda into d by small d. Right? This is the position. So if I just take the first bright and second bright, second one is, see, if I write put n is equal to 2, so I get, no, n is equal to 0 is first one, and second one is 3 by 2. So 3 by 2 lambda d by small d minus lambda by 2 small d capital D here. So what we get? We get actually here from here also d lambda by d. So the fringe width of bright and dark fringes are equal. Okay. So this is the expression we have to remember. All right, d lambda by d. So this is beta. This is called fringe width. So we'll just stop it here. So I'll just quickly summarize what we have learned today. We have found out condition for constructive interference, okay, interference, then conditions for destructive interference, destructive, then Young's double slit experiment we have discussed, and experiment, and there we have discussed, like we have found out, okay, theory of fringes or theory of interference fringes and fringe width we have calculated. Okay, theory of interference fringes, that means what? We have found out the position and fringe width, that is the separation between two successive bright or dark fringes. All right, so we'll stop it here. Next day we'll go further with this, and probably we'll be discussing the intensity distribution for this Young's double slit experiment or interference, and we'll do one more small theory here in the interference. Suppose in case of these two rays, if some of transparent, suppose a mica sheet is placed over here, so some extra path difference will be added to this path. So then what will happen? What is the shift or the whole arrangement of this whole arrangement if we keep underneath the water? So what will be the shift in the fringe position, or what will be the fringe width, etc. We'll just discuss. Okay, so today we'll stop it here then. Thank you for your patience. Bye for today.